today about two X-ray missions. So these are X-ray telescopes, and they're used to observe very hot objects in the universe, mainly black holes, which gobble up matter, and neutron stars. And at the same time, I also want to tell you about radioactive sources and X-ray tubes, which we use to test these telescopes on Earth before we use them in space. And it's kind of nice that the same mechanisms which are used to create X-rays on Earth also are then observed in space. So they're kind of the same type of X-ray sources that you see in all different environments. So I actually want to talk about two missions. One is the New Star mission, and that's a space telescope which was launched in 2012 and has been taking a lot of interesting images, and I'll show you some of them. And Excalibur, which is a balloon-borne mission which we have been developing and which we will fly in the near future. But it's a very different experiment, so I can explain that a bit to you later. Before we start, let me do like 5-minute basics. I assume you probably have heard this already a few times. What light is made of. Like light is transport electromagnetic fields, goes with the speed of light, and it's also made of photons, particles of light, which carry energy and momentum. So light is here like carries electromagnetic field, electric field. You put there a charge like an electron, it will be pulled up and down, and it's made of photons. These are packages of energy which transport the electromagnetic waves. And all the many types of electromagnetic radiation, from radio all the way to gamma waves, and in for us most well known is the visible electromagnetic waves, which are like our light waves, and you can see with the eye. Today I want to talk about X-rays, and you know them from the doctors, that you can use them to shine through the body and make images from bones. So X-rays, they have basically the wavelength is shorter, the electromagnetic field oscillates more rapidly, and the photons have much more energy than individual packages of light. So if you get too much of them, you can get cancer from X-rays. The other thing which is interesting, you know that if you heat things up, they shine and they emit at different types of light, and the more you heat them up, the more energetic get the photons. So if you have something like the sun, which is on the surface something like 5,000 Kelvin, then you emit visible light. If you have something like a human body, it emits infrared light. And extremely hot objects emit X-rays, and these are actually the hottest objects in the universe emit X-rays. So that's why it's so interesting, because you can observe black holes and neutron stars, which are so hot that they thermally emit X-rays. Just by being hot, they emit emission. So just one picture here to exemplify some properties of light. So this is an image taken with optical light. And then if you look at infrared light, so which is lower wavelengths, then the same image is this one here. You can switch it. So infrared light, there are a few interesting things. First, you see that the person itself, like the hot regions, emit infrared light. That's thermal emission, and just by being hot, it emits. So you see, for example, he has hot skin and a hot hand, but colder glasses, and then they emit less. So the other thing which is kind of interesting, that this infrared light goes through a plastic bag, which optical light does not. X-rays also go to plastic bags. That depends on then the properties of the atoms inside the matter. So different types of electromagnetic radiation can go through different types of matter, and whatever is hot emits a lot, and whatever is cold emits much less. So for X-rays astronomy, the X-rays come close to black holes. If just you have a black hole which is sitting there and emits very little or nothing, but it doesn't emit a lot. But if it's close to a star, then it can get some of the mass of the star, and so the black hole has typically a mass of like something like 10 times the mass of the sun, and is in orbit with another star, which is can have a similar mass or less massive. Similar mass, but this one, it can then gobble up the matter, and the matter goes like going down the drain. It goes close to the black hole, it heats up a lot, and it gets so hot that it emits X-rays. So it's the star, for example, may be hot enough to emit blue light or ultraviolet light, emits also a few X-rays, but these black holes, they emit really a lot of X-rays. There's, for example, a famous black hole, it's called Cygnus X1, a few thousand light years from us, and it emits 40,000 times as much energy in X-rays than our sun emits in visible light. So the matter gets extremely hot, and even though the black hole has a diameter of like 20 kilometers, and this accretion disk is also very small, it would kind of fit into Forest Park almost. It emits 40,000 times as much energy as does the sun for a very small region. And we can see that in X-rays. So the black hole sits there. The other kind of objects are neutron stars, which have like a radius of 10 kilometers or so also very small objects, and they have also a very hot surface that they also emit thermally X-rays. So if you want to study these objects, which have the most extreme gravitational fields and the most extreme matter densities, you have to get an X-ray telescope. Unfortunately, the X-rays are absorbed in the atmosphere, and so one needs balloons or spacecraft to observe these X-rays. So the most extreme objects in the universe thermally emit X-rays, and so if you want to study them, X-rays are the thing to look for. What I want to talk a bit about is hard X-ray astronomy. So if you have read about X-ray astronomy, it has been done a lot for the last 30 years. For the last 30 years, people have used imaging X-ray telescopes to get images from cosmic objects. What's pretty new is hard X-rays, so the X-rays have a bit more energy. Instead of having like 5 keV or 2 keV, they have 10 or 100 keV, and these X-rays, they can penetrate matter much better. So at a doctor's office, you usually use these hard X-rays, and they are now also used for astronomy. And better now because we have better telescopes. So one of the telescopes I want to talk about is NuSTAR. That's a project which was led by Caltech and JPL and was launched in 2012. One exciting thing, or one really good thing about this telescope, it was one of the first telescopes where the principal investigator is a woman. That's Fiona Harrison here. And so she designed the experiment and then is shepherding it since it has been launched in 2012 and leads the science, the science working groups working with the data of that experiment. And then, so this is called NuSTAR, Nuclear Spectroscopic Telescope Array. You see it has mirrors here, and they focus X-rays which come from black holes. It focuses on some detectors. So that they do X-ray imaging, and you get images of the object you observe. The other telescope I want to talk about is Excalibur. That's like a balloon-borne experiment, so you have to go above the atmosphere to see the X-rays from black holes and neutron stars. And it uses also a very similar mirror here, and then inside there's a bit different detector assembly, and show you that show that to you a bit later. So this does not images actually, but that's what we call polarimetry, and I will explain to you what that is. But it's a different type and a new type of getting information about black holes and neutron stars. This is a balloon-borne experiment, and we will go to Fort Sumner to fly it. We actually flew it last year, but the pointing didn't quite work, so we have to go back and fly it again. And we'll go in 2016 fall again to fly that, and then it flies for 24 hours at 125,000 feet altitude. And it takes pictures of something like 2 black holes, 2 neutron stars, and 1 active galactic nuclei, like a supermassive black hole. So that will happen in a year from now. We are also working on a proposal together with Fiona Harrison to combine the mirror technology of this NuSTAR telescope with the detector technology. And this project we call Polestar, just sounds very similar to NuSTAR. And we proposed that, and the proposal is under review. 20 teams have submitted a proposal, and 1 will be selected, or 2 will be selected in the first step in May or June. So we're very nervous to see what comes out of that. If we get it, so first only 2 are selected, then there's a 1-year study phase, and after that 1 year, 1 experiment will be selected. one experiment then will get $175 million to build that thing. So very much hope that we will get that experiment, Polestar here. It will be like NuSTAR. The only change is that we change the detector so that we can do polarimetry instead of imaging. So what we kind of say in the proposal, it's 71% built to print. You can use exactly the same plans to build it, but it's 100% new science because we do this polarimetry, which I can show you. So these are two projects, polarimetry, and this is another one. Four news that I wanted to briefly comment on. So the thing is that we have mirrors to make images with X-rays. Usually they go through us, but you can also focus them and make images. And so if you have like optical light going through a thin mirror, it will be reflected, but if it goes through X-rays, it will just go through the mirror. And so what one can do is to have grazing incidence, so the X-rays only skim the surface, and then they get reflected. It's like you can reflect light in a pond or so in the surface. In a similar way, the X-rays can be reflected if you hit them at a grazing incidence, like under 1 degree to the surface. This kind of explained by the optical properties of the material, how they depend on wavelengths, and you get this kind of total reflection once you in the X-ray regime for certain materials. So X-ray mirrors look a bit different than other mirrors. They're not just like parabola, but they're made of many shells. And then the X-rays come from a source far away, and they hit the mirror on a grazing incidence and then are focused, and you can get a real image of it. And it has many, many different shells. And the first experiment of this type was launched in 1980 by Giacconi. And he got a Nobel Prize a few years ago for starting this X-ray imaging. This was, at that time there were soft X-rays, now we're going more to hard X-rays. But soft X-rays are still interesting. So we have these mirrors that we can show you. This is a NuSTAR telescope, and it has the two mirrors here. This is a star tracker camera here. And it was fitted in a little container to go on a rocket and to be launched. And then it had an expandable boom. So there was kind of, in space, it expanded to a size of 10 meters, because the mirrors have a 10-meter focal length. And these are the mirrors of NuSTAR. So it's 256 layers. And they're 0.2 millimeter thick glass, coated with platinum carbon and tungsten silicon layers. And so the X-rays go in, and then they skim the surface and get focused on the focal spot 10 meters away. So it's a beautiful mirror. One of them costs like $1.5 million, and they're made with many, this is 256 shells, and then you evaporate different materials on them to make them reflective in the X-ray regime. So here you see a little bit, like just a zoom in, where you see the different layers, and the X-rays go in and then skim the surface and get focused. This shows the expandable boom. So that was a big deal actually to make that, because they built the first one for $6 million and it didn't work. And then they had to do a second one and third one, and the third one worked finally. But you want to be really sure it worked. So this one in the end was very reliable. And these are the detectors. We also developed them at Washington University. They're called cadmium zinc telluride detectors. They are light silicon detectors, solid state detectors. Photons going in create a charge signal. But instead of silicon, which has atomic number 14, this has atomic number 50, so it's like 4 times heavier atoms, and they absorb X-rays much better. So this is the new detector technology, and this makes it possible to get an image of a focused X-ray. So we calibrate these with radioactive sources, and what we usually use is 152 europium, 63 neutrons, 63 protons, 89 neutrons. And so there are nuclear processes in the inner sanctum of an atom in the nucleus, but they prompt the reconfiguration of the electrons, and then they emit X-rays. So it's inside the atom, which is like 10 to minus 10 meters, about 10 billionths of a meter, is this tiny nucleus. And this prompts changes in the atom, which lead to the emission of an X-ray that we can use then and see if the mirror works and the detectors work. And so we have little sources of that, and a lot of them, and carry them around, and every detector is tested with this europium source. So what happens inside the atom is that the nucleus, which is made of protons and neutrons, captures an electron, and also then emits a neutrino. But the electron is captured, and subsequently, a bit later, an electron which has more energy takes the place of the electron which was captured. And when it takes that place, it makes a state transition and emits an X-ray. So this usually things in the nucleus, you get very energetic gamma rays out of when they come really out of the nucleus. But if the processes happen for the electrons which surround the nucleus, you get X-rays out of this process. So we use these a lot of X-ray sources. You can just see the electrons make a state transition and emit X-rays, and it kind of has to do with the electron changing state and also moving around. This shows a spectrum of europium-152, and you see many different lines. And we are mostly interested in these low energy lines where then an X-ray, an electron changes state and emits these X-rays. And we use them to check the detectors. The other type of X-ray sources I wanted to mention, they make use of that electrons if you move them around and accelerate them, that they emit electromagnetic waves, light or X-rays. So if you move the electron up and down, you get it's like a little antenna, and it emits waves which move away with the speed of light. And you can do this with an antenna, and you get radio waves. To get X-rays, you have to move the electrons really fast and accelerate them really fast. And you do that by bombarding them or shooting them on a surface. And then on the surface, they get slowed down a lot and then emit X-rays. So what we use in the lab are these Bremsstrahlung tubes. We have here a tube. Heat a wire, it emits electrons, and the electrons get then accelerated by high voltage to something like 50,000 volts. And then you impinge them on a target, and they get slowed down and emit X-rays. And so this is a very different process. It emits also X-rays, but it's not a radioactive source. And if you go to the doctor and he comes here and makes a little picture of teeth with a little machine, it has a Bremsstrahlung source inside. So if you switch it on, the high voltage switch on, creates a lot of X-rays, and you switch it off and it doesn't do any X-rays anymore. So this is what is used. So it's a different process. It's basically made with 3 electrons, which you kind of jerk around and make them accelerate a lot to create X-rays. Another thing which is interesting is that these are not treated as radioactive sources. So if you buy one, it's a completely different process, because radioactive sources are federally controlled, and there's a federal protocol of what you have to do to get in a radioactive source. These X-ray tubes, they are state controlled because they don't count as radioactive material. But you can make a lot of X-rays. But this is kind of just a different way for interpreting this emission of X-rays, and that's just taught that to my students, so I wanted to mention that today, is that you can, instead of saying the electrons comes close to the nucleus and changes its direction very quickly and emits X-rays, you can also see the same process and see that in the rest frame, in the reference frame of the electron, where the nucleus comes. And so the nucleus of the material comes to the electron, and the nucleus carries electric fields and also produces magnetic fields. And all this together looks like an electromagnetic wave, and the electron then scatters its electromagnetic wave. So an alternative way of seeing this process of Bremsstrahlung, where electrons produce X-rays, is that they scatter the electromagnetic field of the nucleus. It's kind of interesting. And this was the first time was done by Weizsäcker and Williams in the 30s or 40s, that they analyzed this Bremsstrahlung process as scattering of nuclear electromagnetic waves. So this shows a spectrum of a Bremsstrahlung tube. You can actually purchase some of them and just put them in the USB port of a computer and have an X-ray source. And then you can put it somewhere and get an image. You shouldn't do it too much because it gives cancer. So but you see, you get some, this is a spectrum here, and then you also get some characteristic lines. And this is very convenient for, I think I wanted to, almost forgot here. So this nice thing about this one is, just remember that this Bremsstrahlung is a scattering of electromagnetic waves. And scattered waves are always polarized, and I will explain that later. But Bremsstrahlung tube actually makes polarized X-rays. It's not just arbitrary, and I'll show you what that means in a minute. So for testing the X-ray mirrors, you put a Bremsstrahlungstube in a 100-meter long tunnel, and on one side is a Bremsstrahlungstube where you kind of accelerate the electrons and smash them into a target, and on the other side you put then the detector, and in front then you can put the mirror and see how much of the X-rays are actually collected by the mirror, and you can take the images of the mirror. And so that was done with our mirror and also with the Nooster mirror. This is the X-ray source. It sits inside. You put a lot of lead around, so it doesn't, so it's safe. And then it goes through the vacuum tunnel for 100 meters, and then you can put the mirror and focus them and get X-ray images and get the angle resolution of that X-ray telescope. So are there also, these were the X-ray sources in the laboratory, are there also similar sources in space? It turns out there are really similar sources to these two types of very different sources, but they are in space. And the first one I wanted to show you is the supernova remnant, CAS-A. So CAS-A was a star that exploded something like in 1670. Usually if a star explodes and it's pretty nearby, a few hundred light years away, you would see it at the night sky. And many of the supernova, like Tycho discovered one, and you could just see it, and lots of people would see it when it exploded. So it's kind of funny that this supernova, which was very big, supernova type 2, wasn't observed by anybody. So there are no records when it really exploded. But just by looking now how the remainder of the star expands, you can extrapolate and say it's more or less 1670 when the star exploded. So it was a very massive star, and it's one of the brightest objects in the night sky for radio telescopes. So there's this matter, these are the outer layers of the star, and they are thrown off into space, they run into space, and then they heat up. And in this they shock the medium, we say, and as they heat up, they accelerate electrons, and they emit then radio waves. And this is a radio picture of this supernova remnant. Looks like a brain a little bit. These are the outer layers of the star flying away. And at the center, there's usually you can find a neutron star which is left over by the stellar explosion. And you can see that in X-rays actually. So this was for the first time now also imaged with the Nooster satellite, the one I showed you in the beginning. And the special thing about the Nooster is that it can measure these very high energy X-rays which come from nuclear decays. So this supernova, it's a lot of protons are converted into neutrons, a lot of nuclear processes take place, and in these nuclear processes a lot of radioactive material is produced. And one of the radioactive material is called titanium-44. There's explosive oxygen burning and alpha-rich freeze-out of silicon burning. So there is nuclear reactions which usually only happen inside the sun, but they happen in the explosions, and they create new elements. And some of them are unstable, like 44 titanium, and it decays on a timescale of 60 years. And people already a few years ago, they were able to detect X-rays and gamma rays from this titanium-44 decay. And now it's for the first time to actually image those with the X-ray mirrors that I've shown. So the next image, this just shows the spectrum, the energy spectrum, where you see like this function of energy of photons, the energy of photons. And at the highest energy you see these emission lines, and these are the lines from radioactive titanium-44 as it decays. It also captures electrons, and some electrons reconfigure, and they emit these X-rays, very energetic X-rays, which would can only detect now with this telescope and focus and take an image. So if you look at the image, it's like a multi-wavelength image with false colors, and information from different telescopes is shown in different colors. So soft X-rays are shown in green, red, and yellow, and you see kind of this brain-like thing of the supernova remnant, which is a few light years in diameter. And but now for the first time, this blue image shows actually the X-rays from radioactive decays of titanium atoms, and you see them here. So it has kind of, it was a bit surprising that this titanium is pretty much scattered through this exploding star. people had expected that it would either be much more concentrated at the center, or that it would be kind of funneled into into an outflow, like two regions which with concentrated titanium. But it's kind of all together all over the place. So that was kind of surprising, but it's the first image of a supernova remnant in radioactive, like seen through radioactivity. And the thing which is, for example, new is that you really see all the titanium-44, because all the titanium-44 is unstable and will emit this light, while earlier image only saw the hot material which got heated up enough to emit. But this radioactivity sees all the atoms which are unstable, and these are all of them. So you see all the titanium-44 irrespective of the temperature of the emitting atoms. It's kind of some new thing about this image. There are some conclusions here from this observation. So the titanium-44 is synthesized near the boundary between material falling onto the star as it explodes, and this material ejected in the surrounding medium. These observations probe the really inner core of how the explosion takes place, and they show all the titanium-44 irrespective of the temperature. It's highly asymmetric, as you saw. It's not just like looks like a random pattern of titanium-44, which is kind of funny, but it's not bipolar. And so people had expected it would either look very compact or bipolar, that stuff falls onto this core and then comes out in two bipolar outflows, we call that, which you see often when some young stars have these outflows. We call them jets. But what we see is actually not neither of these two possibilities, just a random, like more irregular pattern. So the conclusion is that this core sloshes around before it explodes. As the explosion takes place, you have some motion of the inner part of the star, and as it explodes, it makes an irregular explosion. So there's some information about the explosion of stars. We wanted to show you the second. So this was like radioactive material, and nuclear processes inside the atom trigger this reconfiguration of electrons which emit X-rays. Wanted to show you the second type of producing X-rays is by changing the velocity a lot. And so the example is a galaxy cluster, and this is the most famous galaxy cluster by now. It's called the bullet cluster. So it's a galaxy cluster. It's made of two actually subclusters, and you see each of these points are galaxies made of 300 billion stars. But they have all galaxies, they have like hundreds of these, and they make two clusters, and these two clusters merge. They kind of circle around each other and go through each other. And in optical, you see the galaxies, but the kind of fun thing is that there are a lot of more masses actually between galaxies. It's the interstellar medium, we call that, and that emits X-rays because it's so hot. And it emits these Bremsstrahlungs X-rays actually. The gas is so hot, the electrons smash into the gas, and then they emit X-rays as Bremsstrahlung. So if you look at the same thing in X-rays, it looks completely different, because you don't see the galaxies, but you see a big blob of hot gas, or two blobs of hot gas. So if you see that in, probably you have seen that in a previous Saturday lecture, but in X-rays you see these two blobs of hot gas instead of seeing hundreds of galaxies. And this gas has actually 5 times more mass than the galaxies. It's a lot of mass, and it's normal matter made of baryons, protons, and electrons. And they emit X-rays by because it's so hot, it has a temperature of something like 1 million degrees or so. This cluster is so famous, and this is a completely different talk, but it's so famous because you can not only see the galaxies and the hot matter, the hot normal matter, but you can also see the dark matter that you normally cannot see. So dark matter, for some reason, is not electrically charged. It doesn't send off electromagnetic radiation, but it makes up most of the energy of the universe. But you can see the dark matter because it deflects light rays. And in this case of this bullet cluster, there are so many galaxies in the background that you can analyze the distortions of the images through the gravitational force of the dark matter, that you can reconstruct where the dark matter is sitting. And this is shown here, where you see a composite, and you see that the galaxies are shown, you see an optical light. In X-rays, you see the Bremsstrahlung X-rays here in purple. And then in blue, you see dark matter, just reconstructed from analyzing the images of galaxies behind the cluster. And so this is a beautiful image because it shows in optical the galaxies, the hot gas, which has much more mass than the galaxies. But then through the gravitational effect, you also see the dark matter, which has even more, 5 times or 10 times more mass than the hot matter. And which is something which for some reason we actually have it on Earth, but it doesn't interact with us. If you look at dark matter, at a cubic centimeter, the energy density is the same as a third of a proton. There's actually a lot of energy density in every cubic centimeter of dark matter. But it's of stuff that doesn't interact with us and goes through us all the time. But there's one particle, more or less like one third of a proton in energy density in every cubic centimeter of this dark matter. Okay, so this was all like this was actually imaged with previous X-ray telescopes with new, so you see galaxies, see the Bremsstrahlung X-rays, and you see the dark matter. With NuSTAR you can get also these images, and because it has these hard X-rays, you can analyze the thermal properties of the gas much better. And so people are looking at exactly how hot it is. And then the galaxy cluster here, as the two clusters merge, the gas flies through each other and the gas heated by something we call shocks. So you can analyze the shocks with the help of this NuSTAR telescope and with the help of the X-ray images of these hot blobs at different X-ray energies. Yes? Yeah. So that was all I had for NuSTAR. Just to summarize, you can create X-rays by accelerating electrons, so we call that Bremsstrahlung with X-ray tubes, or with radioactive sources. And exactly the same happens in deep space, and we can take radioactive images of supernova remnant, or Bremsstrahlung images of very hot matter, for example, of galaxy clusters. So I wanted to show in the next is that polarization, that's something what we do now here. I work at the university. So the waves which make up light, they transform the electric field. And if you put a charge into it, it will be moved around by that electric field. We call it polarized if this electric field just goes up and down or left or right. We call a wave unpolarized if all directions are in there. So polarized light, the electric field just goes up and down or left or right or diagonal, but it just goes in one direction. While for most light, it goes in all directions. And maybe you know that from polarization sunglasses, they only pick out one direction of the light. They have little structures in it, and they allow only light of one direction to pass through. And this is a bit complicated, but there's one thing I wanted to show you about polarization, that whenever something reflects, it gets polarized, the light gets polarized. So bear with me through this slide, it's a bit complicated. So electrons, if you move them up and down, they emit an electromagnetic wave, and it goes into what we call a Hertz dipole pattern. So like an electron goes up and down and emits to its sides. So this is shown here, where you see kind of the intensity, and the color encodes the intensity, and it goes to the side. That's like the emission pattern of an antenna, where the electrons go up and down. So to the sides, you get a lot of electromagnetic waves, not up and down. And to the sides, they will be polarized. The waves, the electric field goes up and down all the time. So a dipole emits polarized waves. Now, if you have like electromagnetic waves hitting a window, for example, the waves get deflected. And so if the wave is polarized up-down, the electrons will move up-down. They all work like little dipoles emitting this pattern, and it will emit a polarized wave. If this is for one polarization direction, let's say we get sunlight, which is polarized also in the other direction, so it is perpendicular, the little electrons that work like antennas, they go like in the other direction, up and down, but the kind of interesting thing is that they emit the dipole pattern, they emit to the sides, and they don't emit in the direction of this light beam. And so this light beam will be polarized because only one type of dipole emits. This other type of light won't be reflected in this direction because the electrons or the little antennas oscillating that direction won't emit in this direction because it's a forward direction. So scattering polarizes light. kind of, when you have the light from a window which is reflected, that's polarized, or the light from the sky is polarized. The blue light from the sky, as it gets scattered, is polarized. Reflection polarized light. So I just want to show this. This is like a picture of a pond, and this reflected sunlight. The sunlight is unpolarized. It's made by in the sun, electrons oscillating in all directions. But as it gets reflected, it gets polarized. And then you can put on your polarization sunglasses, and if you put your head in the right direction, you can get rid of this polarized light by putting your sunglasses in the perpendicular direction. So you can, if you put your head in the right direction with polarization sunglasses, you don't see the reflected light, but you see better the light which kind of bounces off the fish, which is not polarized. And it's not polarized because you have these different colors and the atoms that so it's not a nice reflection like on that surface, and then you don't see the polarization of that light. So if you put on your polarization sunglasses, you see the fish and not the reflected water, the reflected light, because you kind of eliminate the polarized light. So there is you can gain something by putting on polarization sunglasses. You get more information. And the same happens for black holes. You have an instrument which is sensitive to polarization, you get additional information. Just like maybe you have seen James Bond, an old movie, where he had polarization sunglasses. And instead of tilting his head to get his polarization line to filter out the white light and to see through a glass, he had these little lever arms there, and you see that he changes the little lever arms and turns around the polarization. And then he looks into a window, you only see a reflection, he fine-tunes his glasses, and then he sees a beautiful spy, like behind there, a Russian spy, talking, but he can't look because he fine-tuned his glasses there. So polarization has information, and you can get something by making use of this. So we do that with this Excalibur experiment, where we have a similar mirror as the new star. It's made of 255 shells, in our case aluminum shells, and there's some coating. And we focus the X-ray on our instrument. The instrument, next slide will be 2016. The instrument, so as new star, you focus the X-rays, but in new star you just take a picture. You just have a detector with pixels, and it detects where the X-rays hit it. In our case, we focus the X-rays onto a stick, and then the stick scatters the X-rays, and the scattering direction depends on the polarization. So the X-rays scatter perpendicular to the electric field direction. And in this way we can measure this polarization, which nobody else has measured yet. It has only been measured 30 years ago, or 40 years ago, for one astronomical object, the Crab Nebula. But using these X-ray focusing mirrors and using the new detectors, we can now be the effect of 100 more sensitive. And with a similar experiment, we can see the polarized X-rays from a good number of black holes and neutron stars. So, and then the X-rays, they get geometrical information about the sources, which are too small to be imaged. So if you see an accreting black hole in a new star, it would just be a dot, because you would need an angular resolution of a micro arc second to resolve it, and the angular resolution is an arc second or a few arc seconds, or actually for new stars an arc minute. But so you don't have the resolution to see that black hole because it's only 15 kilometers and it's many light years away. But with polarization, you do get information of how much light scattered. And this tells you something about the geometry of the black hole, which you cannot get otherwise. Even though you don't have any imaging, but you have the polarization. So this is a new instrument, and we developed that like 5 years ago, and then we built it with the money from the McDonald's Center for Space Scientists. And once we had built it, NASA said, oh yeah, that works. And they funded us to fly this balloon. So we have these detectors, they're the same detectors as our new star using telluride. They're read out by ASICs, these are little amplifiers. And these ASICs, they have to be developed. So this one has 32 amplifiers. And it amplifies the signal which is created inside the detector within a microsecond. But making the ASIC, unfortunately, costs $2 million. This one ASIC. We have to develop it. 1, 2, 3 people have to work for a long time on it. So we were very lucky that a group at Brookhaven National Lab shared their ASIC with us. So we got their ASIC and we could use that with our detectors, which we do here at Washington University. And we put them together and get the entire detector here. So this basically are detectors, and they surround this stick, and the X-rays are focused on the stick, then they scatter, and we detect them with these detectors. And the direction of where they scatter tell us about the polarization. This is a full polarimeter, it's like this size. The X-rays come through the little hole onto a stick, surrounded by detectors, and this is electronics to read out the detectors. This polarimeter goes into a big crystal of cesium iodide, which shields it from energetic particles. And this goes then into a little pressure vessel, which is in the focal plane of the X-ray mode. It's like we rotate everything, so we get rid of error sources. If the detectors are more sensitive in one direction than the other, we kind of average over that. And this shows electrical engineer, undergraduate student, and postdoc, Brian, Paul, and Fabian, with the experiment. You see a motor, turns it around, and it's a shield, it's red